Hey there, ladies and gentlemen, boys and girls, humans of all ages. This is Mr. Dickin here, and today we're going to be discussing graphing systems of linear inequalities. You guys hopefully do remember, of course, systems of linear equations, or systems of equations in general. That's when we have two or more equations being graphed at the same time. Now, at some point, if you want to pause the video, if you need to jot any of this down, please, by all means, feel free to do so. And then you can always just press play when you're ready. So, the big things to keep in mind when it comes to linear inequalities are the symbols being used. Now, just like one variable inequalities, if it is a strictly less than or strictly greater than, the given number is not included. So for instance, if I said x is greater than 7, the number 7 would not be valid there because 7 is not greater than itself. Anytime you have a strictly less than or strictly greater than, you're going to use a dashed line to represent those relationships. On the flip side, if we had a situation, I'm making this up, like x is greater than or equal to 5, well, then that tells me 5 is included. So less than or equal to, greater than or equal to, those are called inclusive inequalities. So it includes that cutoff value. When we graph these, we're going to graph them just like we would a regular linear equation, so a regular old line. However, let me change this here. However, we are going to have to determine, am I using a solid line or am I using a dotted line? And then we have to use some shading. So normally, when it was one variable, we would shade to the left, we would shade to the right, depending on what we were dealing with. Well, with these, we're going to be either shading above the line or below the line. So here we have a dotted line with shading, if you can kind of see, this is the shaded region, with shading above that line. Well, dotted line tells me it's going to be one of these two, and if it's shading above, it's going to be a greater than. Here I've got a solid line, so I know it's going to have the or equal to portion, and it's shaded underneath, so that tells me it's going to be a less than or equal to. Little trick to remember the less than, if you take your hand, make it look like an L, kind of pinch the L together, shaboom, you got a less than symbol. Let's see some examples, shall we? We shall. All right. So first, we are going to find the solution to the system. Now, the solution is just going to be the graph, the shaded region of the graph. These are currently in standard form, and I absolutely could graph them from standard form. However, I personally prefer good old-fashioned slope-intercept form, y equals mx plus b. The only difference here is it's not an equal sign anymore. It's some sort of an inequality. So if I divide by a negative at any point, I have to remember to flip those around. For the first one, to get y by itself, well, I just need to move this 3x to the other side. So I could add 3x to each side. So this would be 3x plus 3. And I didn't need to divide by a negative anywhere, so that just stays as less than. Down here, I'll move that 1x. Remember, there's an imaginary 1. Not imaginary, should not have said that. An invisible one, let's say. Next to the x, so we're going to move that to the other side. This becomes y greater than or equal to negative 1x minus 1. So with this first line, there's no underline there, so I'm going to be using a dotted line, and it's a less than, so I'm going to shade below it. So let's graph this line. I've got a y-intercept of 3. My slope is going to be down 3 over 1, down 3 over 1, and I can do this until I get bored with plotting points. If I want to go backwards, I go up 3, backwards 1. I said before I'm using a dotted line, so I'll use my straight edge here, connect with a dotted line to the best of my ability. It's not going to be perfect, but nothing ever is, whatever. Ooh, that one got really rough. And then what I like to do is I like to make a little note to myself that, hey, we're going to be shading underneath. So real nice and lightly, I'm just kind of marking little shade marks down that way. All right, the next one we deal with is y is greater than or equal to negative 1x minus 1. So I'm going to put my y-intercept down, and I'm going to go down 1 over 1 as dictated by the slope. Now, with regular equations, we cared where these things intersected. With inequalities, it's not as pertinent. It's not the primary goal. Ooh, I guess I should be accurate and throw arrows at the end of these. What am I doing? All right, we have to do a solid line here, right, because it had the little underlined portion. So we're going to do a solid line. Come on. Good enough. And it was a greater than or equal to, so that means I need to shade above this line. So I'm going to real nice and lightly kind of make notes of where that would be. And as I'm looking at it, it appears that this right here, this is the region in which the shadings overlap. So that would be my solution set to this system of inequalities. Any point anywhere within this region would work as x and y values down here. Now, if I tried selecting, for instance, this point, -1, comma, whatever that is, 6, that would not be a solution because it's on a dotted boundary line. If it's on a solid boundary line, you're good to go. Dotted boundary line, not so much. All right, let's do another one relatively quickly. This one's got 3, but please don't fret. The exact same process follows. I like to put it in slope-intercept form, so let's go, that's supposed to be an arrow. Let's go y is less than -x plus 5. This one's already good to go, and this is going to be a vertical line. Anytime you have y equals a number, that's a vertical line. All right, so I got a y-intercept of 5. 1, 2, 3, 4, 5. My slope is -1, so I'm going to go down 1, over 1, down 1, over 1, down 1. You get the point. Get the point, and as I'm writing points. It's funny. Okay. This is going to be a dotted line because I'm not seeing the underlined portion. This is a strictly less than, so I connect with a dotted line. Let's see if I can get this done. Not my best work, never is. Okay, and then see, that was a less than, so ultimately the shading is going to be going underneath that area. So I'm just going to kind of very nice and lightly make notes of that. All right, next up, 2x minus 2. So y-intercept is -2. Slope is going up 2 over 1, up 2 over 1, up 2 over 1. We are going to have a solid line because this is a less than or equal to. So a solid line to connect these. Arrows on the end. And since that was a less than, that dictates the direction of shading. So I'm shading underneath the line. Now when I say underneath, I just put my pencil anywhere on the line and go down. So it appears somewhere down here. This is where the overlapping is kind of happening. Lastly, we have y greater than -4. Let's see, -4. 1, 2, 3, 4. Oh, that would be an x equals. What am I doing? Oh, I've led you astray. Oh, my Lanta. Ignore that earlier. I'm sorry. That should be a horizontal line. My bad. My bad. Okay. So y greater than or greater than -4. 1, 2, 3, 4. And it's going to be a horizontal dotted line. Horizontal dotted. Horizontal dotted. And we are going to go ahead and throw arrows on each side. It was greater than, so we're going to shade above this line. Right now, with all the mess, it kind of appears that this right here, this region, is going to be where all of the overlap happens. So any point within that region or on this section of the solid boundary line would work for that system. All right. Next up, some good old-fashioned word problems. Writing inequalities based on a word prompt. If you need to pause the video here to read through this, and then we'll carry on, by all means, go for it. You are typically going to want to look for a few key phrases. Specifically, anytime you see minimum or maximum, that's going to give you a clue. Or if you ever see the phrase at least or at most, that's just another way of saying at least, a minimum of this, at most a maximum of this. So here we have Tom's company needs to hire a minimum, boom, 20 workers. All right, keyword. So that's the same as saying at least 20 workers. Some are working in factory 1 for $1,000 a month. Others are in factory 2 for $1,200 a month. The total salary of all workers should be within $30,000. Within $30,000. So within, that's kind of establishing a maximum value, right? We can spend less than $20,000, sure, or sorry, $30,000, but we cannot go over it. So first thing I'm going to need to do is I want to find something that has a less than or equal to 30,000. And then I want to find something that has a greater than or equal to 20 somewhere. And as I'm going through, it looks like A works, cool. Let's see here. This guy's backwards, so that doesn't work. B's out. And then C, yep, both those inequalities are backwards. Cool. Process of elimination, it's got to be A. Got to be A. Let's go ahead. Let's do one more, and we'll call it quits. Okay. You want to learn Chinese. You have to complete at least. So we have a minimum value. So at least 8. So anything more than 8 is okay, but 8's the absolute minimum. Reading test and listening test within 2 hours. Within 2 hours. Okay. So within 2 hours, that means 2 hours is the maximum. I should see less than or equal to 2. So 2 hours. All right. It takes you 20 minutes. We got minutes and we got hours. Units are not the same. Tell you what, instead of 2 hours, boom, 120 minutes. Problem solved. Okay. It takes you 20 minutes for a reading test, 10 for a listening test. Which linear inequality works? Okay. Let's see. I should see a greater than or equal to 8. A is backwards. B might work. C is backwards. Oh, hey. Spoiler alert, it's going to be B. And then if we go through, I should see a less than or equal to 120. Hey, yeah, it works for B as well. So for this scenario, we could almost say that X is going to represent the reading, right? And then Y is going to represent the listening portion. So those variables, as established, would match here, right? Combined between reading and listening, we have at least 8 tests. And then between the time spent, right, 20 minutes per reading, 10 minutes per listening, we're staying underneath or within 2 hours, 120 minutes. All right, so that's pretty much all that we've got. As always, don't be shy when it comes to questions. If something does not make sense, please, please, pretty, please, let me know. Good luck, have fun, be safe.